Good morning, participants. Good morning, ma'am.
Morning.
Welcome to the second day.
Madam, only 23 have joined, 24. They are joining, so I think
Yeah. We can wait for some time.
because they're joining continuously.
Okay.
Huh?
Fine.
Wait for another 2-3 minutes.
Okay, ma'am.
Because we have to give the attendance also.
Yeah, ma'am.
Join. Good morning, Sumati. Good morning, Jagat Kumari Madam.
Good morning, ma'am.
Good morning. ,32 have joined, which is 50%. Maybe another 1 or 2 minutes and we can start.
Yes, ma'am.
Maybe a minute more because we'll respect people who have joined on time. Maybe a minute
Yeah.
more, that's it.
Yes, ma'am.
Yeah, so good morning, everybody. And I think we had a very intense session yesterday with Dr. Matt Santamoris, which was on expected lines, but not so intense. Like, I think we can look at every slide of his, and each slide we can make a PhD out of it. It was that intense, which is actually very good that we got uh, such a stellar academician to speak with us or to speak to us. So today I will be talking about the various indices which is used to measure heat stress, and also case studies. See, I am not doing my PhD on this topic, but it's an area of my interest. And what I have done to understand what I am interested to know, those two case studies also I will present. So I will share my screen. Yeah, can you see my screen?
Yes, ma'am.
Is it
Yes.
in full slide mode?
Yes.
Right.
Yes, ma'am.
Okay. Yeah. And 1 minute. Is the slide moving?
Yes.
Great. So
Yeah.
good to go. Right. So today we will see heat stress indices used in researches and also case studies. When I say case studies, these are two pilot projects or pilot work done by me in this area of understanding. So today we will just see, we've had too much of heat stress in my first lecture and also the first part of Sir's lecture. So just briefly, like a recap, what is heat stress? What are the various heat stress indices? And what is the history of heat stress, so that we don't get confused. See, when I was studying, we had learned about effective temperature as a very good way, and then we heard about operative temperature, but we don't use those anymore. So, what is the history and what are the predominantly used methods, especially in the current context? And then the two work that I have done to understand heat stress, this is what we will see. So, if you see, when the human body is not able to release the heat that it is producing because of any reason, because of heat from the external factor or our own metabolic activity, then heat stress can occur. And because of this, the body's inner core temperature can increase, and so many other things can happen because of that. Our heartbeat increases, we get foggy, or we feel sick, nauseous, irritable, etc. So as a result of this, the body stores heat, leading to loss of concentration, sickness, and things like that. And sometimes it can cause fainting and also death. So that is the reason why we are even looking at heat stress as an issue. And also, like how I said, it's not something visible, and therefore to declare it as a disaster takes time, because there is no physical evidence. Now, what are the factors that contribute to heat stress? This is important. One is radiant heat source, either standing under the sun, standing next to the furnace, or standing next to the cooking stove on a warm day, causing high temperature. So, exposing ourselves to high air temperature, exposing ourselves to high humidity. These two I have reiterated the very recent issue because of heat stress, how mortality has happened in Chennai during an air show. Strenuous physical activity can cause heat stress. We all know that. And therefore, we know the difference between doing a physical activity in a AC room and a non-AC room. And then direct physical contact with hot objects. When I say direct physical contact, I don't mean conduction. I mean something like being close to a furnace, or say these along the roadside they make chapatis and dosa and paratha, no? So that is what I mean by saying direct physical contact with hot objects. Now, if we look at what are the various heat stress indices, the IMD or Indian Meteorological Department defines heat wave as we have already seen. If the temperature is more than 40 degrees centigrade in the plain, and in the hilly area if it is more than 30 degrees centigrade, and what is a severe heat wave when the temperature exceeds 46 degrees centigrade, or when the average increases by 6.4 degrees centigrade, then we say it is a severe heat wave. So yesterday we saw that, so I'm not going to reiterate it. Heat waves in India normally occur between May, June. These are the primary months which we have to be cautious, because the heat builds up even by March, but then it peaks in May and June, so we need to be careful about that. So what is heat stress index? So now we are coming to the main part, which is heat stress index. So heat stress index, or HSI, is a measure that combines factors. Maybe sometime it's temperature, humidity, air movement, and radiant heat, because various kinds of various measures they consider various factors. But normally temperature, humidity, air movement, and radiant heat as a combination, how do you feel? That is called as heat stress. And this helps us to assess the physiological impact of heat on humans under different environmental conditions. So sometimes the temperature may be only 50 degrees centigrade, but someone may feel like their skin is even getting cooked. That hot they may feel. That is because of the combination of all of these. You should not look at this in any one factor in isolation, like temperature in isolation. So, and sometimes air movement, warm air, if it if it falls on a person, oh sorry, when warm air, a person, warm air blows on him, again heat stress index comes into play. Even though the temperature may not be 50, it may be say 42 degrees centigrade. So why do we use heat stress index? To evaluate thermal comfort or discomfort in indoor and outdoor environments. Also to predict the risk of heat related illnesses such as heat exhaustion, heat stroke, or even fatality. Now this is very useful in occupational health and safety, especially for outdoor workers like construction laborers or agriculture workers or people in the defense. Also, it helps to develop guidelines for safe exposure, including rest periods and hydration plans. So what I mean by rest period and hydration plan, you will see in the case study. If somebody is working for 2 hours, the heat builds up, and then it is advised that that person should not work for the next so many hours. He should take rest and allow the body to dissipate the heat. So to understand all that, heat stress index is needed, and it is important in public health planning, particularly during heat waves or extreme weather conditions. So we need it during these times. Now let's see what are the various heat stress indices. Now the heat stress index is a single value, and this value combines 6 climatic factors to show how hot an environment feels to the body according to Fanger. So Fanger has his own definition or calculation of heat stress, where it is a combination of dry bulb temperature, black globe temperature, wind velocity, wet bulb temperature, metabolic rate, and clothing insulation. Now, to compute each of this, there are certain formulas that Fanger has given. So, based on that, we can arrive at these values. So, this heat stress indices, they help to assist and set safe limits in design and workplaces. Though widely studied, there is still debate over which index is more accurate, because we need to also understand the purpose of this index, why we are using, in which context. That is very important. So all that we will see. It also relates to how people feel heat, both physically and mentally. What happens to someone who is exposed to heat for long hours? How does he feel? Then assessment of thermal stress and translation of the stress in terms of physiological and psychological strain is very complex. Heat stress index is related to thermal sensation, how you feel, and how it is related. It is related on this 9-point scale, where neutral means the heat stress index is considered as 0. And here vasomotor reflexes are compensable. Then slightly warm. Even when the thermal sensation is slightly warm, how do you feel? We do feel comfortable, or we are able to manage this scenario, and that is around 10, between say 10 to 20 heat stress index. When the thermal sensation is warm, how are you feeling? I'm feeling warm and it's slightly uncomfortable for me now. And then the body tries the sweat evaporation method, and then the heat stress is called as is at 20. Then when someone says they feel hot, then it becomes uncomfortable. It's very hot today, I feel very uncomfortable, and heat stress goes between 40 to 60. And then the ultimate is very hot, during which we feel very uncomfortable, and it is uncompensable heat with a heat stress index of 80 and above. So this is how feeling is also calculated, or feeling is also monitored. And let's see the history of heat stress indices. Now, heat stress indices have evolved probably over 80-90 years, because scientists have attempted to try to understand and quantify the impact of the thermal environment on human health as well as performance. So these indices try to integrate various environmental parameters and physiological variables to understand and assess how heat affects the body. So here we will see a timeline based overview of how heat stress indices have evolved. So between 1900 to 1940s, we had these four. So in 1905, wet bulb temperature was considered as one of the as a good indication of heat stress, which means it was one of the earliest method where they tried to link temperature with humidity to understand how anyone can feel uncomfortable. Then in 1916, Kata thermometer was introduced, and this measured the cooling power of air through convection and radiation. 1923, the effective temperature. This is what I think most people in my generation, or people who follow manual of tropical housing, they would have heard about this effective temperature word, where temperature, humidity and air movement is combined into a single value. So a single value comes as a combination of temperature, humidity and air movement. If anyone wants to know, you can see that book gives a very good understanding, or a very basic understanding of what is effective temperature. And also between 1932 to 1948, CET, corrected effective temperature. So refinements were made to effective temperature and called as corrective effective temperature, along with certain new indices like resultant temperature or predicted 4-hour sweat rate. So details of this, if you want to understand, you can see that book. Then came the development of physiological indices from 1950 to 1970 had 1955 said heat stress index. This focused on heat loss, heat gain equations. Then the WBGT or wet bulb globe temperature. This became the most widely used index because it was simple and had applicability of field. And I also understand or know this primarily compared to anything else. I use this primarily. 1970 predicted mean vote came, which was by Fanger, and this became a major breakthrough because it integrated 6 climate factors and human factors to predict thermal comfort. Then came the SCT in 1973, which is standard effective temperature, where clothing and metabolic rates were also added to environmental variables. Further, up to 2000s, some refinements came because we had indices like effective heat strain index, cumulative heat strain index, and physiological strain index. These were also introduced because these focused more on physiological response like heart rate, sweat rate, and core temperature. So when you are following any of these methods, you should understand the purpose for which you are using this computation of heat stress, because the factors that are involved in each of these methods are different, and that is related to the reason why or the purpose why you are computing. Now, in the last, say, past 20 years back, new indices like environmental stress index and Wallace's wet bulb dye temperature, these provided alternatives for field-based quick assessments. You can have meters, place it, and without any computation, get the values. Now we will see what happens in the modern period. So today, what do we use? Today, indices like WBGT, these are used primarily for military, sports, industry, globally, these are used. The PMV and set method is common. WBGT is also used for indoor thermal comfort. PMV and set is common in indoor thermal comfort standards like ASHRAE, ISHRAE, and so on. And we have a PSI, which is used in research and physiology. And these indices help us to guide building design, workplace safety, climate adaptation strategies, and public health alerts. So what are these? We will see. And how you feel again now is brought down to a 7-point scale, where 0 is neutral and then +1 is slightly warm, +2 is warm, +3 is hot, -1 is slightly cool, -2 is cool, and -3 is cold. So within this range, if someone indicates this range, then it is comfortable and good to go. Otherwise, some no intervention is needed. So I have already told this, but I thought I will place this, and then we can see the wet bulb temperature. It combines air temperature and humidity. Kata temperature is cooling rate of a heated object, the rate at which it cools, which depends on the parameters of air. Effective temperature combines air temperature, humidity, and air velocity in a nomogram. So from a nomogram, we can find out what is the effective temperature. Equivalent temperature is air temperature adjusted for humidity. CET, corrected effective temperature, again is effective temperature, but it also adds the factor of radiation. Then operative temperature combines air temperature and mean radiant temperature. Thermal acceptance ratio, it uses physiological responses, and that is primarily used for occupational studies. So this is a very important column you have to see, based on which you can select which method you want to follow. Then index of physiological effect uses skin temperature and sweat, and this is used for human physiological strain. very sticky, feels sticky, then how do you measure that? Then corrected effective temperature again, which came back again in 1946 with a revision, is a revised corrective effective temperature model, which is this is what is the Bedford scale. The 5-point or 7-point is used in building science. Then the predicted 4-hour sweat rate, the components are sweat loss over a 4-hour period, and it is used for work planning in heat, like people closer to furnace or heat stove. Resultant temperature combines air temperature, radiation, and airspeed. Again, this can be used for indoor thermal environment. Then Craig index is not really well documented, but it is more for military purpose. Heat stress index is used for metabolic rate. It combines metabolic rate, air temperature, and relative humidity. WBGT, wet bulb globe temperature, uses wet bulb globe temperature, dry bulb temperature. Then Oxford index combines metabolism with environmental conditions, and discomfort index combines air temperature plus humidity. And this is used for weather forecast. For weather forecast means they, okay, temperature is 32 but feels like 46 and will be a very warm day. Thermal strain index combines heart rate with body temperature. So this is more for physiological monitoring. Then we have the discomfort index, which is a modified version of Thom's, and then this is more for human perception, not in terms of actual numbers. Then the cumulative discomfort index, this uses time weighted discomfort index. Then index of physiological strain uses core body temperature. Index of thermal stress uses clothing and metabolism combined with the other environmental parameters and is useful for military heat stress. And then this was established by Baroj-Kivani. Heat stress index combines metabolic heat versus heat loss. Prediction of heart rate uses what work they are doing, the intensity of workload along with temperature and humidity. And then effective radiant field uses mean radiant temperature component. PMV, predicted mean vote, uses temperature, humidity, air velocity, clothing, and activity, which is used in building design and also by ASHRAE. And then we have the prescriptive zone, where a range of comfortable environments has been given as design guidelines. And then the new effective temperature keeps on evolving itself over time. You can also have your own new effective temperature standard. Then the WBGT, which came in 1971, was a simplified version of the earlier WBGT. The humid operative temperature uses operative temperature plus humidity. Predicted body core temperature combines metabolism with heat balance. Skin wettedness uses evaporative heat loss. Standard effective temperature uses air temperature, humidity, radiant temperature. Predicted heat rate is used for health monitoring. Skin wettedness uses sweat rate and body cooling. And fighter index of thermal stress uses core temperature, heart rate, and sweat. Whereas effective heat strain index uses core temperature, sweat, and heart rate and is used for occupational stress studies. Then the predicted sweat loss considers metabolic rate and humidity, and required sweating, SW required, considers sweat required to maintain heat balance. Predicted mean vote modified uses, it is adjusted for various climate and is used for comfort studies. Cumulative heat strain index uses core temperature, sweat, heart rate over time. Physiological strain index uses core temperature and heart rate. Modified discomfort index, and so on. So there are so many which are there, and we have the, oh god, what's this? Yeah, so there are so many indices which have developed over time. But what is of use and relevance, or what is predominantly used today? We will see that now. So the WBGT, or wet bulb globe temperature, this is used predominantly as it estimates heat stress by considering temperature, humidity, radiation, and air movement. And this is used for occupational safety, and it finds a mention in ISO 7243 in the occupational safety standards. It is also used for assessing sports, military, and factory environment. So, what are the factors or parameters involved in this? Natural wet bulb temperature, which is humidity, radiation component, ambient air temperature. And for this, formula is given how to compute the WBGT, because you can see it. This is natural wet bulb temperature, which is the humidity, and then this is the globe temperature. This is the natural wet bulb temperature, and TA is dry bulb temperature, DBT. So if you have the globe temperature, dry bulb temperature, and wet bulb temperature, you can compute the wet bulb global temperature. So, and then some corrections. This is for outdoors, and then for indoors, some corrections are there. So with this, we can find out what is the wet bulb temperature, wet bulb globe temperature in that environment. Then we have the predicted mean vote method, where it is an indicator based on a model by Fanger, and the model was based on several experiments which were conducted in controlled environment experiencing different environmental conditions. When they were asked, how do you feel, and then their feeling or acceptable range of predicted mean vote of occupant is considered, and based on that the standards have been evolved, or the parameters have been used. So the parameters used here are air temperature, as I have already mentioned twice, air temperature, mean radiant temperature, air velocity, humidity, metabolic rate, and clothing insulation. And this is used for indoor environmental in green buildings, and ASHRAE standard 55 ISO 7730 also uses the PMV method. Then we have the standard effective temperature, which is defined as the equivalent air temperature of an isothermal environment at 50% relative humidity, under which a subject wearing clothing standardized for the activity concerned has the same heat stress. That is, his skin temperature, everything is same, and thermal regulatory strain, how sweaty he feels or how warm he feels, as in the actual environment. So the analogy is the relative humidity versus absolute humidity. Now, outdoor standard effective temperature is an extension of this, which includes solar radiation, infrared radiation for outdoor applications. And the factors that they consider are air temperature, mean radiant temperature, air speed, humidity, clothing insulation, and metabolic rate. And this is applied for dynamic comfort analysis, transient thermal modeling, and adaptive comfort studies. So be careful about what you want to study, and based on that follow the system. The third predominant one is the PSI, physiological strain index, which measures the physiological stress because of heat, which is based on heart rate and core body temperature. And therefore, this is used more for worker health and military training. For these purposes, this is used. So I won't go into the depth of it. unless you are interested in following any of this. And then the UTCI, Universal Thermal Climate Index. This is, see, this should be, this and WBGT should be of interest to you if you are working on a thermal comfort. So this is used primarily for outdoor thermal comfort, UTCI, urban climate studies. And so outdoor thermal comfort, if you want, you should look at UTCI in greater depth. So UTCI is the equivalent air temperature that would cause the same physiological response under reference conditions. So it's a comprehensive outdoor thermal comfort index which uses air temperature, mean radiant temperature, wind speed, relative humidity, clothing standard and metabolic rate. Then you have the PET. So I'm not going to get into the detail of it because again, it's up to you whether you want it for urban microclimate or open space design. More for, so this is also for outdoor. If you are interested in outdoor, then you can look at it. And this is the, so what all, again, it's the same set of parameters, but used in different way because its applications are different. Now, the heat stress index. So, heat stress index represents the percentage of the person's heat storage capacity used under certain environmental conditions. So, this compares the body's required evaporation for heat balance to the maximum possible evaporation in that environment for it to cool it down. So, this again used in occupational heat stress and industrial settings, and also to understand worker safety. Now what I have done is, from this I have picked up what interests me. I have done two small pilot projects. These are not even case studies, they are pilot projects. So in this first one, what I have done is, it's an assessment of heat stress index of rural houses in heat wave prone hot humid climate of Andhra Pradesh, India. Word hot humid is very it's very too fluid, I feel. Chennai is also hot humid and Chennai is warm humid, so this is okay, that much is better. So a study is conducted here in 5 rural houses in a heat wave prone area which is called as Vallabhapuram in Andhra Pradesh. So it's somewhere here, Vallabhapuram, closer. And what we have done is, field measurements were conducted on 5 houses, and this is collected during a warm part of the year, which is in April. So in hot humid regions like Andhra Pradesh, just being outdoors can induce heat stress due to high temperature and humidity. Being indoors also leads to heat stress because in low socio-economic houses in rural India, they do not have the gadgets or apparatus to cool them. So in this study, we have assessed the indoor WBGT for a moderate activity in rural houses of these 5 houses. So the sample houses are selected like this. The 5 houses are located in Vallabhapuram, and that's a typical rural village which is located about 25 to 30 kilometers away from Vijayawada. And May to September becomes very hot. So we have taken this in April, luckily, because it was very difficult with to collect this data was difficult. So we've taken it in April with outdoor average during that time was about 44 degrees. Now these sample houses were selected on this basis. The houses should be similar form, similar size, similar microclimate, and the outdoor spaces should also be similar and the activity use should be similar. But 4 of these houses had different walling material but same roofing material. And one sample house was built with conventional material. So 4 houses plus one conventional house was selected, and all these houses were along one street within a distance of say 200 meters. So we assume that the microclimate did not vary much. So from the indoor climatic data of air temperature, air velocity and relative humidity, the WBGT is calculated using the Bernard and Ormagny method, and this followed the climate chip calculator. Now the WBGT or indoor analysis of data was done to compare WBGT of all 5 houses under conditions of moderate activity and WBGT of house 1, 2, 3, 4, which means houses with same roof material but varying walling material and roof made of reed. WBGT of house 4 and 5. 5 is the conventional house, which is 9-inch brick wall with a RCC roof. And this house number 4 is brick with reed roofing. So these were also compared. And then this shows clearly what I had meant in terms of building material for walling, flooring, roof, etc. And then the indoor climatic parameters were collected with instruments, and what did the result show? So this study actually compared how much work people can do inside these 5 different houses based on the WBGT values, which shows heat stress levels. So indoor work includes basic household tasks like cooking, cleaning, sieving or folding clothes and things like that. So house-wise, the results showed that when you had reed walls, when the walling material was reed, which is actually called rail gaddi, this is grass grown along the rail tracks closer to this place. Now, before 12 o'clock noon, work allowed is only 25% of the time because the house is so warm that they should not work beyond that. After noon, they can work for 50% of the time. But people living there felt uncomfortable after 8 a.m. Though they felt uncomfortable, they could still work for 25% of the time till the afternoon. House 3, which is made up of brick wall with reed roof. This is reed wall plus reed roof. Between 10 a.m. and 1 p.m., they could work for 75% of the time and they should rest for 25% time. Whereas houses 2, 4 and 5, only 50% time they can work and 50% rest should be given during the day. This is because the body reaches heat stress faster. So among the 4 walling material analyzed in this study, brick wall in combination with reed roof performs better than other 3 walling materials, which is reed, stone, cement, concrete blocks. It shows the least discomfort compared to the other houses and enables 75% of work and 25% of rest time, which is this, which is brick wall with reed roof performs best, and in that we can have 75% work and 25% rest time. Its indoor temperature is lower than outdoor temperature by 3 degrees centigrade to 4 degrees centigrade. In all the other 4 houses, which is made up of walling material made up of reed, stone, cement, concrete block and brick with RCC, work for only 50% of time is possible, otherwise the body reaches heat stress levels. The conventional house with brick wall and RCC roof has higher indoor temperature than the other houses. So we also try to understand what is the indoor temperature and try to compare it. But actually here we are talking of heat stress, so I will skip that part. So we realized that 5 houses is not a great number and we should actually try to do something better. And here we try to in the second case study, we tried to study 17 socio-economic households in the heat wave prone of city of Nagpur. And here the households have varying roofing material like RCC, tin, terracotta tiles, and also varying walling materials in terms of thickness and finish. Again, we have considered field measurements of indoor climatic parameters of all the households were captured using data logger, and indoor WBGT is assessed again using the same Bernard and Pormagni method. The indoor WBGT values are compared based on orientation, walling material, thickness, and roofing material. So, data we have collected from 17 houses, but comparison is only apple to apple, say with respect to houses of same orientation, because we cannot get the same combination of all, say 12 roofing material all oriented in the same direction. We cannot get that. So this is work in progress, but for whatever it's worth, I thought I will tell you all, share with you what I have done. These cases are selected to include again similarity of area, microclimate grouped according to orientation. So these 5 orientations we have classified the houses as: brick wall with varying thicknesses and plaster with same roofing material. Brick and mud walls are primarily utilized in the neighborhood. Different roofing materials with same wall material and thickness. RCC, tin, terracotta roof tiles, these are primarily utilized in these neighborhoods. And then these the data is collected inside using the loggers. And then again we have done this what shall I say, documentation. Only of 12 I am showing for lack of time. And then the result shows that WBGT of 17 households for various work percentages. So here the task performed includes household chores like cooking, house cleaning, water filling, sieving, and mild body movements. So this graph shows that households with tin roof records highest WBGT values, and household with terracotta roof tiles, these record lowest WBGT values during afternoon, that is from 1 o'clock to 4 o'clock. But both tin and terracotta roof tiles, they record lowest WBGT values from 4 o'clock to 7 o'clock in the morning. All remaining households accommodate their WBGT values within these extreme ranges during the daytime. So then according to the questionnaire survey also, tin roof is considered to be a better alternative to terracotta roof tiles based on maintenance factor, waterproofing, and cumulative economic feasibility. So our concern may be to provide them with the best indoor condition. But when you ask the users, their criteria of selecting a building material is not just thermal comfort, because they may say that no, we may be able to spend those discomfort hours with certain, but there are other factors because of which they choose the materials. So the WBGT difference during evening and night hours is also considered, and then it is seen that WBGT values of tin roof, it drops below that of terracotta roof tiles with a difference of at least 1 degree centigrade. This indicates that performance of terracotta roof tiles exceeds tin roof in terms of protection offered to inhabitants from rising temperature, but inhabitants prefer tin roof for reasons of maintenance, waterproofing, and also economic feasibility. Now, if we look at work limits, then the work limits and intermediate rest in every hour, which we have analyzed for a moderate intensity of work, shows that with tin roof and unplastered half brick thick walls, WBGT values reach 50% work during afternoon from 1 p.m. to 4 p.m. Whereas in conventional households, the work activity, especially by women folk, happens primarily during this period, and that is a issue of concern. Thus, the occupants are exposed to more heat stress during morning hours than remaining hours due to increase in activity levels. Similarly, when you use tin roof, they have higher WBGT values reaching threshold for continuous work. This indicates that occupants staying inside the tin roof household, they are subjected to very high stress levels during the month of March. So you can imagine what would happen in the month of May. So when roof is made up of terracotta roof tiles and one brick thick wall with plaster on both sides, this has the lowest WBGT value. Other cases with terracotta tiles have lower WBGT values than RCC and tin roof cases, especially during morning work period. So on and so forth. So this with this chart we can discuss so much if we are able to understand the combination of the roof and the wall material of these 17 cases. If I try to explain that, then all the time will go off in explaining the combination of materials only. That is why I have not gone into the depth of it, but more for the methodology to understand what combination of wall and roof material would be convenient for the people so that they get how much percentage of work versus how much percentage of rest during which part of the day. So this is very important, especially when you are dealing with occupational health analysis. So with this, I will stop the class because I also have to close it before Sir joins. Has Sir joined? Sir has not joined, isn't it? Okay, we'll have time for quick one or two questions. Prashanti, are you there? Can you please note if Santa Morris Sir is joining, and when he joins, Sir has joined. Okay, he's already there. So, if there is a quick question, we can take it. Otherwise, I think we are right on time closing this for Dr. Santa Morris to join and start his presentation. Maybe we could take the questions after his presentation. Sir, welcome, sir. Would you like to start your presentation now? Sir, Dr. Matt Santa Morris, would you?
Yes, yes. Hello, hello, hello.
Hello, sir.
Hi, everyone. Thank you so much. Okay, let's share my presentation.